Okay, so today I want to do path integrals. I want to explain how path integrals are used in quantum field theory. And the idea, as I said, of the remaining few lectures is to try and explain the path integral formalism of quantum field theory, and then to look at gauge theories. Yeah. Okay, so first I want to remind you of path integrals in quantum mechanics that you've probably seen, but in my experience, is a somewhat tricky subject. So I am first going to remind you of that. Okay. So the idea is that we want to understand the time evolution operator, okay, for some time t between a state qi and a state qf. Yeah. Okay. So this is, this is the time evolution operator. It just comes from standard quantum mechanics. Just one second. Yeah. So this is the time evolution operator, and we are going to derive the path integral representation. Okay, so we are not going to postulate it. We are going to start with this evolution operator. We are going to divide the path integral representation. Okay. Okay. So the idea is basically that you have this e to the minus iht, and you separate it into lots of different terms. Okay. Okay, and there are n terms, like we'll take n to infinity later. Okay, and epsilon is equal to t by n. So you have this evolution over a very long period of time, and instead of writing an evolution over a very long period of time, you separate it into lots of small time evolutions. Okay. Okay. Now, in the middle of all of these small time evolutions, you can insert some states. So you can write this as qf e to the minus ih epsilon, and let's see what notation I used. Notes. Qn on the right or qn? Okay, anyway, doesn't matter. Yeah, so you can write this as qn, and you have qn e to the minus ih epsilon, qn minus 1, and so on. Okay, so maybe you have q1. And then you have to integrate over all of these qn's. So if I do this, I have to write this as dq1 to dqn, okay, and I integrate over all of these qn's. So this is a completely, perfectly well-defined thing to do. I started with this. This is equal to this. Let's see how this n is related to. How many did we have here? N minus 1. Is this n is capital N or n is small n? Let's see. I don't know whether we have n plus 1 epsilons or n epsilons. Okay, doesn't matter anyway. Okay, so so this is a completely well-defined thing to do, and we have just written the time evolution operator from 0 to t. You know the answer is it n or n? Huh? This is n minus 1 right now. Total I wanted well. It does. Let me erase this. Okay, this should be n minus 1. You're saying? Okay, maybe there are n plus 1 terms here. Then okay, let me keep this. Okay, let's try and calculate. We start with 1. Okay, so 1 comes with e to the minus ih epsilon, and you're right. N minus 1 comes with e to the minus ih epsilon. Okay, fine. You're right. Let me have n plus 1 terms here, okay? And then epsilon is t by n plus 1. Okay, now it's correct. Okay, so yeah, okay. So you're right about that. Okay, so this is we've inserted some complete set of states, and we want to look at this. Okay, okay. Now let's try and understand what are the possible terms we could have inside H. So one possible term we could have inside H is that we could have H is maybe some function of G. By the way, at this point, a real Hamiltonian will never have a function of q, but this expression I wrote is just, will give me evolution for any operator. So imagine h is g of q and doesn't have any function of p. Okay. So then focus on one of these terms. Okay. Okay, so what happens here? Well, this becomes e to the minus I into g of qn minus 1, right? And then we get a delta function of qn minus 1. Right? This is what the nth term becomes. Okay, but this I can write as e to the minus I epsilon. What's the matter? Yeah. G of qn minus 1 plus qn by 2 into delta of qn minus 1. You see, because qn is equal to qn plus 1. So I can write it, instead of evaluating it at qn, I can evaluate it at the midpoint. Okay. Okay. Now it's useful to also write this delta function in momentum space. So I can write this as e to the minus I g qn minus 1 plus qn. Okay. Into, let me see what sign I used in my notes. 1 second. Have a consistent sign. I plus IP. Okay. So I just wrote the delta function as an integral of p. Here p was not even necessarily momentum. Okay, it's just a representation of the delta function. Although we'll see, it will be useful to think of p as momentum as we go along. Okay, so is this clear? Okay. This is just, everything is a completely well-defined manipulation. Okay, good. Now, let's see. Okay. Now imagine that h is only a function of momentum. Okay. And then I want to evaluate the same expression. Okay. So say I want to evaluate this expression, then how can I evaluate it? Well, I can insert a complete set of eigenstates, okay, in the middle here. P, this is p e to the minus I p epsilon, okay. And then I'll have I can insert some. So I integrate now over p, okay, dp over 2 pi. In fact, there'll be a delta function, so I could have inserted a p prime, but I'll just get a delta function. So I could just write this as p times qn minus 1. Okay. And this, of course, gives you something else, which looks like e to the minus I f of p epsilon e to the I p qn minus 1 dp over 2 pi. Okay. So if h was a function only of q or only of p, then each of these terms gets a very simple form, which is that you just pull out the function of in the case of g, you pull out the function at its mean value, right? And you pull out this factor which looks like e to the ip into qn minus 1. Okay. Okay, good. Now imagine that h was of the form or it's some function which looks like f of p, let's call it h, of pq, which could be a sum or it could be some other function of something. Okay. Then you might have guessed that so let me write a question mark, okay, is equal to h of p into qn plus qn, like the average term, by 2, okay, into e to the ip qn minus qn minus 1 into dp by 2 pi into epsilon. Okay. Remember, every case the term which has the Hamiltonian is getting multiplied with epsilon. Okay. Is this a true equation? Can you think about it? Is it true that this always works this way? Exactly. So P and Q don't commute. So in general, it's not true that this works this way, right? It's not true that if you take H, then you can, if you want to evaluate H epsilon in Qn minus 1 and Qn, that you can just get this matrix element by evaluating H at the midpoint, okay, and then by evaluating, just by Fourier transforming this way. Okay? However, this is true if you while order H. Okay? So if there's a very special case. So this is not true, for instance. So not true. Say H is okay. H has to be a Hermitian operator, but imagine for now, okay, H was Q to the n p, okay, or Q to the n into P to the m. Okay. If H was Q to the n into P to the m, then how do you evaluate this expression? Okay, you could when you want to evaluate this expression, you basically only want to evaluate the first order term in epsilon, right? So you could evaluate this expression, but what you would get would be something which looks like, this e to the minus I h epsilon, you would write as 1 minus I h epsilon to first order in epsilon, right? And then when you evaluated the expectation value of qn into h epsilon, q to the n p to the m qn minus 1, what you would get would look like, I have the two n's here, sorry, let's call this q to the r, p to the s. Okay. Then what you would get here would be qn to the power r. So h is, this is an operator. Okay. I'm just emphasizing it's an operator because right now, it's not commuting. So what you'd get here would be qn to the power r, okay, times, and then you would get again qn times p hat to the power s times qn minus 1. And this indeed you could write in this way, right? You could write this as qn to the power r into p to the s integral e to the ip qn minus 1 by dp by 2 pi. This you could write this way, but notice, now you have an asymmetry between n and n minus 1. What appeared here was qn to the power r. You could have written s as this way plus another term which looked like p to the s times q to the r. Say you wrote s this way, now h this way, then it became Hermitian. But now you have to evaluate the other term, and the other term privileges qn minus 1 to the power r. So now what will happen is, there will be a similar calculation you can do, which is qn p hat to the s q hat to the r qn minus 1 looks like qn minus 1 to the power r times integral p to the s e to the ip qn minus 1 dp by 2 pi, right? So look what I got here. What I got here is now that for this particular value of, for this h, which is a Hermitian h, so it's an allowed h, okay, the answer that I'm getting is something slightly different. What I'm finding is that e to the minus I h e epsilon when h is approximately equal to, see, the one term will just go for the right. Okay. So I can write this as e to the minus I times q to the n times p to the r, q to the r, qn to the r times p to the s. And then there's another term here which looks like p to the s times qn minus 1 to the r. And this is integrated with e to the minus I p. So I would find an expression that looks like this. Okay. But this expression is not the same as evaluating this h at the average, which is qn plus qn minus 1 by 2. I have, in this case, I have a symmetric term where you have qn here and qn minus 1 there. But, I could have written other forms of h. Maybe this is one particular form. Maybe there are other h's which have some q's sitting in the middle. Okay. So in general, this equation is not true. Okay. What I wanted to show here was, you would have liked this equation to be true, but this equation is not true in general. Is this clear? And it's not true precisely because of this operator ordering issue. And depending on how you order the operators, it's not necessary that this h picks up the value of q at qn plus qn minus 1 by 2. Okay, it could pick up the value either at qn or at qn minus 1 or something else. Okay, okay, good. So this is a genuine problem, which has to do with how you go from the classical theory to the quantum theory. In the classical theory, this h, you would not have written this way. You would just have written it as twice of q to the r times p to the s. Okay, so there is some ambiguity when you go from the classical theory to the quantum theory, because if you have some classical function for the Hamiltonian, what should you put here? Okay, this is the usual operator ordering ambiguity. Is this clear what I said right now? Okay, good. Now there is an ordering which we can choose for h, which makes this formula true. Okay. Have any of you seen this ordering before? Or? Have any of you seen this ordering before? What ordering will make it true? Okay. It's called while ordering. I'll tell you what while ordering is. What does while ordered mean? While ordering of something like this, q to the m, p to the r, this looks like 1 by 2 to the m. This is the definition of while ordering. Into p to the m minus, MCS is equal to 0 to m. Q to the m minus s, p. This is true for operators, of course. Otherwise, it doesn't make any sense. Okay, so it means that you basically sprinkle the q's around the p's in this particular way. Okay, this is the definition of while ordering. Any expression that you have can always be written in a while ordered way. For instance, let's say I told you that h was not while ordered. My h initially was not, say h was q hat squared p plus p hat squared q hat squared. Okay, this is a allowed h. Now I could say this is really my quantum mechanical Hamiltonian. It's not written in the while ordered form. So what should we do? What should we do? So the point is, you see, you can always while order it. And how do you while order it? Well, you realize that to while order it, you would have to add this, okay, plus twice q hat p hat q hat, okay, plus p hat q hat squared, okay, and then there would be a minus twice q hat p hat q hat, okay. Sorry, just one second. No, one second. I'm doing something wrong. This is you can't convert things to while order form. Just one second. Yeah. Sorry, let's start with a simpler example before I calculate it. Okay. Let's say we had q hat p hat, okay, and I wanted to while order this. Okay, then I could have written this as half of q hat p hat, q hat p hat plus p hat q hat, which would be while ordered, and then I could have written this as just one second. Yeah, minus just one second. Sorry, I'm confusing myself about how this is. Yeah. So you could write this as half of q hat p hat plus q hat. Well, no. Okay, sorry. So you could write this as half of q hat p hat plus q hat p hat, which is a trivial identity. Okay, and then you could write this as half of q hat p hat plus p hat q hat, okay, plus a commutator of q hat with p hat. Okay. These are all just identities, and then you would have written this as half of q hat p hat plus p hat q hat, and then you would just have a plus minus I by 2 or plus I by 2 plus q hat times p hat. So you just have a plus I by 2. Okay. And so now you've written this as a while ordered expression. You've written this as the while ordering is this is correct. So you've written this as while ordered of q hat p hat at the expense of putting an additional I by 2. Okay. Now let's go back to this and try and do the same thing. Let's start with q hat squared p actually, rather than starting with the symmetric term. I think I can write this as 1 by 4 q hat squared p hat plus q hat squared p hat plus q hat squared p hat plus twice q hat squared p hat plus q hat squared p hat. And then I can try and convert these guys into 1 by 4. So I can write q hat squared p hat is equal to q hat into q hat p hat q hat plus q hat p hat. And then this becomes this q hat p hat q hat plus I q hat. So I can write this as this expression, and same for the q hat squared p. I have to commute this through 2. Let's try and commute this. And this we can write as p hat q hat squared plus just check my algebra right now if while I'm doing it. So S q hat times p hat, q hat p hat minus, yeah, and this gives you twice I q hat plus p hat times q hat squared. Is this correct? This algebra? Just check my algebra, please. So if this algebra is correct, then we can write this as 1 by 4 into q hat squared times p hat plus twice q hat p hat q hat plus twice I q hat plus p hat q hat squared plus twice I q hat. Okay. So we can write this as while ordered. If this algebra is correct, just check. I think it should be okay because we don't q hat squared p hat plus 4 there's no 4 plus I q hat. Yeah. Okay, so we can write it as the while ordered form of this. You can of course do the while ordering for the other case, right? Which would be where you had q hat squared p plus p hat squared q hat squared, and that would look like also the while ordered form of q hat squared p, but I think with a minus I q hat. Okay, and therefore at least in this case, if you wrote q hat squared p and you wrote a p hat q hat squared, that would already be while ordered. Okay, so you can convert any polynomial into something that's while ordered plus possibly lower order polynomials. Okay, you could of course play this game for a polynomial which had a q hat cube p hat squared. Okay, and the game is just you have to commute things, and so as to put the terms into while ordered form as I did here. Okay, and you are left with some additional remainders, maybe lower order polynomials, but every Hamiltonian can be written in a while ordered form. It's exactly like normal ordering, it's just a different ordering where we're ordering the p's and the q's in some way. Okay, it's not necessary, by the way, that you choose this ordering. You could choose a different ordering where you could have said I'll put all the q's to the left. If you put all the q's to the left, then that formula would not be correct, but you could get a formula where you had p of qn instead of, right? Or you could put all the q's to the right, in which case you'd get a formula where you had q of n minus 1. This is some symmetric choice. The while ordering just makes sure that the symmetric choice works. Okay, with the while ordered choice, you can see that this formula does become correct. Okay, so I want to make 2 points. One of them is that which is what we checked with these simple computations, any Hamiltonian can be put in while ordered form Okay. This is one by commuting. Remember, when you do this, the form of the Hamiltonian that you get might not look exactly like the form of the Hamiltonian you started out with. You might end up adding lower order terms, as you can see, if you played this game. Okay. The second term is with this, when H is while ordered, the formula above becomes true, which is the point we wrote above. You see why when H is while ordered, the formula above becomes true? Because in the case when H is while ordered, you just get the binomial expansion. In the case when H is while ordered, what we need to evaluate is the expectation value of H this is qn minus 1. This is the expectation value we want to evaluate, right, of H in this. So what does it look like? It looks like the expectation value of, the general expectation value we'll get will be a sum over R and S with some coefficients of something which looks like while ordered term of q hat to the R, p hat to the S. with some coefficients. You see, this is the most if I've written a Hamiltonian in a Weil ordered form, then the most general kind of polynomial I can write is something of this kind, right? With some expressions which look like, with some coefficients which are not important. Okay. But now notice what happens here. This expression, this just becomes 1 by 2 to the r, okay, with of qn to the power r, 1 by 2 to the r, sum over t equal to 0 to r, qn to the power r t, p to the power s, qn minus 1 to the power r minus t with a rct. Okay, and then this is multiplied with a e to the I p qn minus 1. There's an integral here, is dp by 2 pi, and this same sum, there's a sum outside which is not relevant, which is a sum over r and s. Okay. I think this form, yeah, you see, all I said was there's a Weil ordered term here. I substituted the expression for Weil ordering which I had written up there, yeah, and I got this expression. Okay, but you see, this is in fact the expectation value of h evaluated at p and at qn plus qn minus 1 by 2. Okay, because I've separated things there. Therefore, this is for the expectation value of h. If you now look at e to the minus ih epsilon, it looks like e to the minus ih, the classical function, but evaluated at qn plus qn minus 1 by 2. Okay, is this clear what I said? Okay, so there's some choice of ordering. The reason I'm emphasizing this is, you might think that when we go from the classical theory to the quantum theory in the path integral, this is not always emphasized. You have some quantum, you have some you have some classical function, you put it into the path integral, and you might say, well, you had all these operator ordering ambiguities. Where did the operator ordering ambiguities go in the path integral? So it's not like they went away. When we go to the path integral formalism, we always make some tacit choice of how to operator order, of how, and one common choice that's made is the Weil ordering choice, which ensures that these kinds of symmetric formulas become true. Okay. Okay. Is this clear what we said so far? Okay, good. So now we found some general expression, which is, we found that we erased the original expression we had. Stop working. Okay, so what have we now found? We found that the general expression we had, which was q final e to the minus iht q initial, looks like product over q equal to 1 to n plus 1, okay, of all of these expressions which look like e to the minus I times h at qn plus qn shouldn't be q, sorry, n equal to 1 to n plus 1 qn plus qn. No, I don't want n to go from qn. N equal to 1 to n qn plus qn minus 1 by 2, and then p epsilon p. Okay. Notice that the number of integrals I have a large n number of p integrals here. Okay. And we already had, we also have integrals over Qn. We also have an integral over dqn over 2 pi. So if you take this and we have this product over matrix elements. Okay, you take the product over matrix elements, and you also have to do the integral of that over all of these dqn by 2 pi's. Okay, I should write this as a different product. So let's, is the notation clear? We have lots of products which are soon going to go away. We are going to make the notation compact, but let me write it a little more clearly. Okay. Epsilon into qn minus 1, e to the minus I h epsilon. Okay. So we had these integrals over dq1, dqn, okay, of this kind of a product. Maybe I'll write it in that form. Okay, so rather than writing these products. So let me just write it a little more clearly, please. So we have an integral over dq1 to dqn, okay, and then for each one of these guys, we got an integral over pn. Okay, so we get something which looks like, let me just write the expression, and then it'll become hopefully clear. And we have e to the minus IH. The first term looks like QF plus QN by 2, and let's call this Pn, okay, times epsilon. Then we have minus, and then e to the IP QF minus Qn, and there's a dPn over 2 pi. We have an integral here, okay, and then we multiply this with an integral e to the minus IH Qn plus Qn minus 1 over 2 Pn minus 1 e to the I Pn minus 1 into Qn minus 1, okay, integral dPn minus 1 by 2 pi, okay, and so on. Keep going. And the last term you get is an integral which looks like e to the IH into Q1 plus Q initial. Remember, there's a Q initial here, okay, by 2. And there's a P1 here. And this looks like e to the I P1. I hope it's P1 and not P0. Let's see. We introduced Qn with P. Let's see. So we put a Pn into Qn. So Pn is going with this guy. So this will look like P0, in fact, I think. This is all going to be completely unimportant in a second, but I'm just trying to make things as accurate as possible here. So Q1 minus Qi dP0. Okay, we had n plus 1 p's and n q's, but this will of course not be important when we take the limit. Okay, and there are epsilons everywhere here. Okay. Is everyone happy with this formula? You know, it looks like we made something very complicated. Okay? In that, you know, we started with something which looked like a simple expression. Then we broke it up into n plus 1 terms. We inserted all of these terms here. Then we Fourier transformed each of those terms and wrote each of those terms in this form. Okay. So is it clear what's happening here? Okay. You see, this I can write as an integral. You know, it's an integral of a product of integrals. Okay. So what I can do is I can write it as a single integral over all of these guys. Okay. And then I can multiply all of these integrands together as well. Right? So I can write it as dq1 to dqn, dpn or dp0 to dpn. Okay. And then I can write it as e to the minus ih into qf plus qn by 2 into int dn plus h into qn plus qn minus 1 by 2 into pn minus 1 and so on. Let me erase this term now. Let me just keep it since this is the last term into epsilon, and then I have this. Sorry, I just borrowed the term from the upper line into this because it was going to come here anyway. Plus. Okay. And I also have, with all of these guys, I also have an e to the I pn into qf minus qn plus pn minus 1 into qn minus qn minus 1 and so on. Okay. And the last term looks like plus dot 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 into p0. I hope I'm getting my p0s and p1s correct. Yeah, it might be that there's some mistake here, but I think it might be okay. Into q1 minus q0 qi. Okay. So these terms are multiplied with an epsilon, but those terms are not multiplied with an epsilon. Everything is an exponential. So if you like, I could write the whole thing inside a single exponential and just put pluses here. Okay. So notice I have two different kinds of terms. Okay, and I have all of these integrals. Okay. Okay. So far we've just been doing manipulation in various integrals, but everything we've done so far is exact. Okay. There's no loss of any approximation here. Is this clear? Yeah. This is an exact statement for what we are now going to write as a path integral. Okay. Is the manipulation till here clear to everyone? Okay. Okay, good. You see, now you look at this expression and notice that all of these terms are multiplied with a small epsilon. Okay. Now the idea is that you try and take, so this is something that is sorry, let me correct myself. What we did here was correct. It was correct up to first order in epsilon. Sorry, it was not exact. It was correct up to first order in epsilon because when we expanded out that h, we expanded it out and we took 1 by 1 minus ih epsilon. Okay. But except for terms of order epsilon square, what we have done here is completely kosher. Okay. So to make it exact, what we should do is we should take the limit where epsilon goes to 0, okay, and the number of these divisions goes to infinity. Okay. In that limit, this expression becomes exact. Okay. It really gives you the value for e to the minus iht. Okay. Moreover, you see that this thing that you have here, which is just a sum over different h's, okay, you can in fact write as just an integral, okay, of h over time, okay, where time is just, you can think of as just these different divisions of epsilon. Okay. And this here, you might have thought, doesn't look like an integral, but in fact it does. And the way you make it look like an integral is you just divide this by epsilon and you multiply the whole thing by epsilon. And then if you think of this as being a division in, these epsilons as running over different intervals of time, you would write this as, now what I'm writing is formal, as dp dq, okay, into e to the I into pq dot minus h integral dt. Okay. Okay. The correct formula is the limit of the previous formula as n tends to infinity. Okay. This is in fact this formula in the limit that n tends to infinity. Okay. is an exact expression for e to the minus iht. Okay. Sometimes this is written as dp over 2. Okay. What we have here is not an exact, is some formal representation of how this expression, which is an infinite set of integrals, you can in fact think of integrating over all paths from qi to qf but over all paths, not just in position space, but also in phase space, also in momentum space. So you start with some qi, you start with some p0, you have here some other ps. So you have to integrate over all values of the initial momentum, all values of the final momentum. So I can't draw it, but you have to integrate. You have a path in phase space. So the integral is over both p and over q, and you have to integrate this. You see, you have to integrate pq dot minus h over all possible paths in phase space that start at qi and end at qf, where the initial and final momentum is also allowed to vary. So this is a path integral in phase space. Okay. But the exact expression really is the one here. This expression is a formal expression, but it doesn't tell you what's the correct measure to use. Okay. I should have been careful of this. This expression is not a formal expression. It tells you evaluate this, you divide, the path into n parts, and you should really put a measure. And this 2 pi is also important. The fact that you have this 2 pi is important. So you really expect, if you divide, if you do this integral over many small paths and you take the limit that epsilon goes to 0 and capital N goes to infinity, you will get a finite answer. And to get a finite answer, you expect to also keep track of the 2 pi's. Okay. When we write this formal measure, okay, the measure is not very well defined, but you can make the measure well defined by going back to how the path integral was derived, and this is how it was derived. Okay. Sometimes you see the path integral written only in position space as an integral over all paths. I'll now tell you how this relates to an integral over all paths. But in fact, this is how the path integral is originally defined, as an integral over all paths in phase space, not over all paths in position space. Okay, and this is how you get also correctly the path integral measure. Okay, is this derivation clear? The 2 pi is important because otherwise you have an infinite factor of 2 pi. If you don't keep track of it, you'll obviously not get a finite answer for this. There are n 2 pi's, right? Or there are n plus 1 2 pi's. If you don't keep track, if you even keep track, so if you're not careful of the 2 pi's, then you won't get a finite answer for this. So this path integral as it's written, when I first saw the path integral as a student, I would say, oh, this is completely crazy. What does this mean? What does it mean to integrate over all paths, right? What is that? What's the measure? So sometimes you'll see this description, you integrate over all paths, but what does it mean? How do you write a measure over all paths? Well, the correct answer is, if you derive the path integral, you will see that this is how you'll get the measure. So you indeed divide it into n parts, and over all n parts you integrate, but there is a specific factor for the measure, and this is the factor. And this is because you derive it starting with the Schrodinger evolution operator. If I had written 4 pi here, it would not have been the correct factor. Okay, so the path integral is something which is well defined. It's the limit as you take n to infinity with this measure. Okay, but the measure is well defined. When you write it in this form, it doesn't look well defined at all, and that's why I wanted to emphasize this derivation. Okay, so the measure, the ordering, everything is well defined. Okay, good. Is this clear? Okay, now I want to tell you how you get to what might be a more familiar formula, where you write the path integral as an integral of e to the is, where s is the action, over, but just over paths. Okay. So sometimes you will see the path integral written as e. You see, by the way, why this became q dot, right? This became q dot because it was just a division of separation of values. Okay. Now, this is a path integral where h is written as a function of p and q. Remember, the Hamiltonian is a function both of momentum and of position. Okay, and so what you have here is pq dot minus h, right? However, the path integral is sometimes written as a function of the action. The action is not a function of the momentum and the position. The action is just a function of q as a function of t. So the action cares about q dot and cares about q, and it doesn't care about pc. Okay. Now how do we do that? So you can go from this expression that we have to an expression in terms of the action. However, it requires us to make some assumptions about what the form of the Hamiltonian is. Now, it is often the case that the Hamiltonian is of the form that I'm about to write down. Okay, but what we are now going to do, which is write things in terms of an action, is slightly less general. Okay, so consider to be of the form, p squared over 2 plus some v of q. Okay, so it's a form where this is Gaussian. You can put some factor here, some constant factor here, and it won't change anything. Okay, so I'm imagining that this HP has the form p squared over 2 plus v of q. Okay, okay. That's a special form. In that case, we can do the integrals over p. Remember, there's an integral over p and also an integral over q. Okay, for this case, okay. How do we do the integrals over p? Well, the integrals over p are all basically Gaussian integrals. Why? Because you have one factor of p squared which comes from the h, and then you have a factor of p that comes from the q. Okay. Okay. So what is the basic formula for the Gaussian integral? The basic formula is this one, which is the most important formula in path integrals. You should remember this. Okay. So in this case, yeah. Okay. Okay, let me put the mass to be m. It doesn't matter. You could put the mass. I mean, it's some simple factor, but let me put it to be m. With that, we find that a is, just to substitute this. You see, you have this factor which comes from h. Okay, and we'll find that a looks like in that formula looks like I epsilon by 2m, okay? And b looks like I into qn minus qn minus 1. Okay. This is for the nth p integral. Okay. So you just have a sequence of Gaussian integrals. For the nth p integral, you have this form. Okay. You have to be a little careful because this integral is not strictly convergent. Okay. It's not strictly convergent because a here, this assumes that the real part of a is positive. Okay, that's why it's important when you do the path integral to rotate time slightly. Okay. So if you rotate time slightly so that the real part of a, so that epsilon develops a small imaginary negative part, okay, then I epsilon will develop a small positive part, which is what you need for this to be correct. So rotate the time contour slightly. Okay, so you rotate the time contour slightly, and this is important. And this is is also the same kind of rotation we've seen in field theory. Okay? And it'll also become clear in a minute why this rotation is the relevant rotation. Okay, when we look at correlation functions. But to make this integral well defined, we have to rotate the contour slightly. Okay? Another way to think of it is that you rotate the time contour all the way to Euclidean space, and you think of Euclidean path integrals, and then you rotate back to Lorentzian space. Okay? So path integral, sometimes any way to define the path integral, it's always important that you have to rotate the time contour slightly. Often it's done by rotating the time contour all the way so that epsilon just becomes minus I of some other epsilon prime. Okay? And then the path integrals just become nice convergent Gaussian integrals, and then you can do it and then rotate back. Okay? I'll say this again when we come to the field theory. Let's do it right now with a slight rotation. Okay. Then b squared over 4a. This algebra I've done in my notes. I'm not going to try and do it again right now because there are lots of factors of epsilon and i's, and the prefactor just becomes square root of twice pi m. I think this is correct, but you should check if I got this right. Yeah. Okay. So with this expression, what we get is just that qf e to the minus iht qi looks like now an integral over product of n dqn, okay, into e to the I epsilon m by 2 into qn minus 1 squared by 2 minus v of qn plus qn minus 1 by 2. Okay. Okay. And this dqn now comes with a funny factor which looks like m by 2 pi I epsilon. Okay. So we get everywhere a factor of this kind. We had a dp over 2 pi, that's why you got an m by 2 pi instead of an 2 pi n. Okay. Now, this is now the correct measure to do the path integral in position space. Okay. Notice this measure is not as nice as that measure because now the measure itself has an epsilon. But in fact, if you want to do path integrals in position space, you do have to keep track of this measure. Okay. So this we can write as, I'll write a tilde here. This is now you recognize here the action because this looks like m into q dot squared. Okay. 1 second. I should have put an epsilon here. Sorry, not a 2. Okay. The reason this happened is because you see b squared looked like qn minus 1 squared by twice epsilon. So I wrote this as qn minus 1 squared by epsilon, which gave you an epsilon squared, and then I took out one more epsilon out here. Okay. So this you can write as dq times e to the is. What you have here is now s because this is just m of q dot squared minus v. Okay. So this product over all of these n's you can think of as just integral over dt. And so it's integral of dt of m q dot square minus v. Therefore, you get integral of dq e to the is, where dq should be understood this way. Okay, in the discrete limit. Okay, this is the formula for the path integral that is sometimes often written, where you write it as integral e to the is dq. But as it's written, this is a pretty ill-defined formula, just to say, because it doesn't mean anything. What do you mean by integral over all paths? And what it really means is you should take this measure. And where did this measure come from? This measure eventually came from that measure. Yeah. The whole thing is well defined as epsilon tends to 0 and n tends to infinity. Well, the measure is well defined. Why? What do you mean only measure is not well? What is it? Sorry, you have to integrate something with it, right? The integrand also has an epsilon dependence. Correct. Yeah. It's not a product, it's an integral. The measure is not, doesn't float around by itself, right? The measure goes with an integral. It's a measure for doing a particular integral. Yeah. Okay, good. So that is the basic formula for the path integral in quantum mechanics. In fact, the exact same formula I'll go through in quantum field theory. But let me first say something about correlation functions. Yeah. Okay, is this clear what we said right now? Okay, are there any questions about this? I find that students often tend to get pretty confused with this. Okay, so please don't get confused and make sure you're comfortable with all of these things. Okay. Okay. Now we want to understand something else. Now I want to explain what happens if you compute okay, now we have some formula for the path integral. In fact, the formula we'll use for the rest of the lectures on the path integral is the formula that just got hidden, okay, which is that we'll do the path integral as dq times e to the is, okay. Okay, so this was the formula that we just derived. This integral is done over all paths which start with I and end at f in a time t, okay, and you have to integrate over the action for such paths. Okay. What that measure dq was, we wrote in the previous slide. Okay, okay, good. So this is the answer for this. Let's say I now choose to evaluate a slightly different integral. These are some times between 0 to t. What is this in operator notation? Of what? Okay, so so what expectation value is this? Q of T2 and Q of T1. I see, but Q of T2 and Q of T1 might not commute, right? So now what should we do? We write Q of T2, Q of T1, or Q of T1, Q of T2? This is a function, that's it. So in this case, it can't matter whether I write T of T1, T of T2, right? So here it's a function. So this is clearly equal to, because these are all classical numbers. In the path integral, by the way, all operators have gone, right? This is true, obviously, because these are functions. But what's the operator relevance? What do you want me? What do you want to say this is in the operator language? Okay, good. It's time ordered, but there you also get some other factors. So indeed, you know, what I want to now derive is that when you write this in operator language, it can't just be the expectation value of T1, T2 or of T2, T1. But the path integral automatically time orders whatever insertions that you put. Okay, so that's what we now want to see. Okay, so the way to see this is that we say that, you know, we interpret this in the following way. Imagine, say, 0 is smaller than T1 is smaller than T2 is smaller than T, which is the T that we had here. Okay. It doesn't matter how we write it. Okay, we could have written this as T1, T2 or T2, T1. But let's imagine that this is how the times are ordered. Okay, so this is the ordering of the times. Then the way I would evaluate this is I would say, you know, I can do this path integral in the following way. I can first look at, you know, the integral over all paths. So this integral, let me write the limits here, is at q of 0 equal to qi and q of t equal to qf. Those are the limits that I put in the measure here. Okay, that as you said, as I said, precisely you have to make the measure there precise, but this is the limit over paths here. Okay. I can write this as an integral over q of 0 equal to qi, q of t2 t1 is equal to something, let's call it q, what should we call it? Let's call it q1 of e to the is. Okay. Then I multiply this with a q1. Okay. Then I do another integral from e to the is from q of 0. Sorry, let me write it. Q of t1 equal to q1 to q of t2 equal to q2. Okay. Multiply this with q2. Okay. And then I do another integral. I'll write the integrals. Yeah. And I do another integral over e to the is, okay, of q of so this is the integral over dq, integral over dq. I do another integral over q of t2 equal to q2 and q of t equal to qf, which was the original expression that I had, dq. And then I also integrate over these initial values dq1, dq2. Okay. So what I've done is I had a path integral over all possible paths, right, which went from at t equal to 0, this was qi, and here they went to at t they went to qf, right? Now I said here is t1, here is t2. I can instead think of integrals of paths that go from q1 to t1, have some boundary condition which is fixed, which I call q1 at t1. That's this factor. Then I think of paths that go from q1 to q2, which is this factor. Then I think of integrals that go from q2 to q. That's this factor. But remember, I had q of t1, q of t2. So I inserted a q1 here and I inserted a q2 here because I'm multiplying. And then I also integrate over these boundary values. So that's the same as integrating over all paths. Yeah. So is it clear why this is equal to this? Yeah. Is this clear? Okay. But see, for now this, on the other hand, is exactly what we derived an expression for previously. Okay. What does this look like? Well, this looks like qi, okay, times e to the I minus iht1. Okay. Let me put some space, sorry, and I'll write it. I still ran out of space. Okay, is this clear? I wrote it as a function of 3 factors, but each of these factors we know how to interpret them. This is the first factor, this is the second factor, this is the third factor, and then there is factors of q1, q2. So we know how to interpret these factors, right? Okay. Okay, good. So this is, now remember, what is q1 into q1, q1? What is this integral that you have here? This is just the operator q1 hat. Okay. In the path integral, you naturally end up with these operators in the Schrodinger picture. Okay. So we don't end up with operators in the Heisenberg picture. We end up with operators in the Schrodinger picture. Okay. Because we have this basis of q1, and then we are multiplying it with q1, and this basis we just choose at some time. So this guy is just q hat. This is the operator q hat. So what we have now found is that this looks like this operator qf into e to the minus ih. Let me write it somewhere else. Let me write it in a different page. Otherwise we'll get confused. So we found that this expression looks like qf e to the minus ih tf minus t2 q hat ih t2 minus t1 q hat. These are all operators now. Actually, I'm not being so careful now, but I hope there's no confusion. Okay, there was some classical function, but by this time when we write these brackets, it should be obvious they're all operators everywhere. Okay. Huh? What? What happened? So do you see where this formula came from? So there's no q1, q2. The q1, q2 went away. It went away from that formula on top. Okay. So dq1, q1 was equal to q hat, and same for q2. q1 is just a dummy variable there. That's why it became an operator here. Yeah. Okay, very good. But now we can recognize this as some Heisenberg operators. Okay. Now we can recognize, let's say, actually I did something slightly mistaken here. I don't know if you'll permit me to change notation at this point, but okay, let's say the short. Okay, let me just write an expression and I'll indicate the obvious generalization. Okay, so this looks like e to the minus ih t1, and this looks like e to the ih hat into t1. Okay, so what we got here is just q hat of t1, but now written in the Heisenberg representation. This was just a Schrodinger operator. Okay, qi. Okay, what we got here was what we got here was e to the minus ih hat t2, e to the plus ih hat t2. Okay, so we got q hat of t2. Okay, then we got e to the minus ih of tf. Okay, and then we got qf. Okay, imagine. So this is the answer that we got. Okay, I'm now going to generalize the answer slightly. Okay. Here I imagine if we were starting at time t equal to 0 and going up to time t equal to tf. Okay. Imagine we had started not at time t equal to 0 but at time t equal to ti. Okay, then everything would have been the same, but I would have got one more factor, which I'm now just going to insert. Okay. Ti has not appeared, but I just want to write this expression symmetrically. Is it clear why we would get this factor here? Yeah, you would get minus IH into T1 minus TI here. So that TI I'm just keeping here. Okay. So this factor I've inserted just to make it look symmetric. Okay. So this is the expression we now have. And notice that these have got time ordered. Okay. So the operators have automatically got time ordered. If I had written, if the ordering had been the other way around, then I would have got the other ordering. You see, because that's obvious from the way we do the path integral. We cut open the path integral at these times, and then we get these factors of e to the minus IH. In fact, in the expression we got originally here, we just had q hat. We didn't have the operators at any time. So you just automatically got the first time first and the second time second. Okay? So you automatically get later on the left. And that's clear when you just look at the path integral, you start with that expression and try to evaluate it in operator form. Okay. So is this clear? The path integral automatically time orders things. Okay, good. So that's what I want to say about path integrals in quantum mechanics and about correlation functions. I now want to say something about field theory. Yeah. Okay, now we're going to derive an important formula for field theory. Now remember, field theory is quantum mechanics. Okay, so field theory is not different from quantum mechanics. Okay, why is field theory quantum mechanics? Because remember, as I've emphasized many times before, we can always discretize the field to a lattice. Okay. So you can always imagine that you have all of these field variables like these q's which are exactly like the q's, but they live at different points on your spatial lattice. So now what will happen? Well, you'll get the same expression for the path integral that we had previously, except now you'll also have to integrate over all of these field variables at all these positions in space. You're also having to integrate over all paths these variables take in time. So it is as if you are integrating over all, over all paths in space-time, or all configurations the field can take in space-time. So the answer is exactly the same. The answer is, if you want to look at the expectation value of the field to go from phi I at some, e to the minus IHT phi f, okay, where these states are eigenstates of the field. Okay, so they are states of the field, but written in the Schrodinger representation, which we discussed once previously in the class. This is exactly the same as e to the is times d phi, okay, where you put phi of t0, phi of 0x equal to phi I. Remember, these states are just functions. These states of the field are three functions on just space. They are not functions on space-time when you speak of eigenstates of the field. And phi of tx equal to phi f of x hat. Okay, so the same derivation that we did previously tells us that if you want to evaluate this, then you should do this. Okay. So I hope it's clear that we don't have to rederive this again. The quantum mechanics derivation still works. That's because you can always discretize the field, and field theory is quantum mechanics. So what is true in quantum mechanics is true in field theory. So the obvious generalization of the formula that we had is this. Okay. Okay. Now, in quantum field theory, in perturbative quantum field theory, we have often been very interested in computing correlation functions. Remember, the S matrix and so on also had to do with correlation functions of Heisenberg operators of the field in the true vacuum of the theory. Okay, so there is a way to now write down an expression for correlation functions of Heisenberg operators in terms of the path integral, which is an important formula that we are now about to derive. Are there any questions about this formula? Okay. So the idea is as follows, right? Consider these are some points I have fixed by hand, okay, x1 t1 to xn tn, d phi, but with no boundary conditions, where this integral goes over all space-time. So the integral is now integrating over all space-time. I'm integrating over e to the is, and I've put these insertions. Okay. Well, what is this going to look like? This is like an integral that's coming from minus infinity, okay, all the way up to 0, okay, and then or all the way up to t1 or whatever the times are. Okay. So let's set, and then going from t1 to t2. So it's exactly like this kind of a formula. Okay, but the only difference is that the initial time is now in minus infinity, and the final time is also plus infinity. Okay, so what you get here, this is equal to, okay, what about the states here? So let's say we put some boundary conditions at minus infinity. As I'm going to say in a minute, this will not matter. Let's say we put phi at minus infinity, x is equal to phi 1 or something, phi initial, and phi plus infinity x is equal to phi final. Okay, say we put this expression. Okay, good. So what is this equal to? Well, it's equal to phi final e to the power minus I times h times infinity, okay, times the time ordered product of phi of x1 t1, phi of xn tn, times e to the again minus I h times infinity times phi I. Okay. Is it clear why you get this? Okay. Okay. However, notice that this evolution, which is an evolution of an infinite amount of time, okay, will always project you onto the vacuum eigenstate. If you do this in Euclidean space, you will find both these factors will become e to the minus h infinity. Okay. This was going from t0 minus infinity, okay, and this was going from tf to infinity, but you will find that both these factors will just become some convergent factors, and the only term that will remain is the vacuum here. So this is equal to phi f times the vacuum, okay, times the vacuum okay. This factor we know how to deal with. This factor is also the factor you would have got with no boundary conditions if you had no insertions. Okay. Therefore, the general point is that if I divide this by just e to the is with the same boundary conditions, and that's the same as just dividing this. I'm just writing denominator here, but here we know what the denominator is. The denominator here is just phi f omega times omega phi I. So these factors just cancel, and what you're left with is this. Okay. Therefore, that expression is equal to the time ordered product in the true vacuum. This is the full true vacuum of the theory. There's no perturbation theory here. Okay. You see, these boundary conditions are basically unimportant. I could put whatever boundary conditions, or I could integrate, or I could put the field to 0 at infinity. I could do whatever I like, as long as I use the same boundary conditions in evaluating the numerator and the denominator, because they're all going to cancel. That's why these boundary conditions are usually not written, and the final formula is just written in this way, which is an important formula, which I'll just write here. D phi. Okay. So you have to normalize the path integral by e to the is. Sometimes, people might not even write the denominator, by which it's understood the denominator is just set to 1. You normalize the measure so the denominator is set to 1. But this is the formula that we have finally for correlation functions. Okay. This is an important formula in quantum field theory, because remember, I emphasized many times that eventually in quantum field theory, or at least in perturbation theory, these are the quantities we want to compute. This is telling us how to compute them using a path integral. Yeah. Okay. So this was the formula I wanted to derive. Next time, what we'll see is how you get back also just the perturbative expansion of Feynman diagrams that we got using Wick's theorem, how you can get it back using the path integral. And then we'll start applying the path integral to understand electrodynamics, because gauge theories are sometimes more easily understood in the path integral language, although not necessarily. I'll explain also how to do it in the canonical language. Okay. So that's what I wanted to say. Are there any questions about this? Okay, we have 2 lectures left. I could do a third lecture, but it looks like there isn't much enthusiasm for the lectures. So we'll see how much we get in the 2 lectures. But we can stop here if there are no questions.